Hey everyone, welcome back. Quick question to start. What if a computer could try every possible answer to a problem at the exact same time? Sounds impossible, right? That's exactly what quantum computers promise to do. And by the end of this video, you're going to understand how, in plain English, no physics degree required. Stick around, because there's a genuine mystery waiting for you at the very end that even scientists haven't fully solved. Let's get into it. Here's the roadmap. We'll cover why normal computers hit a wall on certain problems, the strange trick called superposition that gives quantum computers their power, spooky entanglement, a phenomenon that bothered Einstein so much he tried to disprove it, why you don't have a quantum computer on your desk yet, what this technology could actually change about your life. And I'm saving one genuine mind bender for the very end, a real unanswered question in physics. So, let's start from the beginning. First, let's meet the humble bit. Every computer you've ever used, your phone, your laptop, even the device you're watching this on, speaks only two words, 0 and 1. A bit is just a tiny switch, fully off or fully on. Every photo, every song, every word on your screen right now is really just billions of these switches flipping in patterns. But here's the catch that matters for everything we're about to cover. A bit has to be one or the other. Never both, never in between. Now, here's the problem. Imagine trying to find one correct combination among trillions of possibilities. The fastest delivery route across 1,000 cities, or the one key that unlocks an encrypted file. A classical computer, no matter how fast its chip is, can only check possibilities one at a time. Guess one, check it, guess the next. For truly massive problems, that adds up fast. To crack certain codes by brute force this way, a classical supercomputer would need longer than the age of the universe. That's the wall classical computers hit. So how do we get around it? Meet the qubit. This is the qubit, the hero of our story. A classical bit is like a light switch, locked at 0 or 1, fully off or fully on, with nothing in between. A qubit breaks that rule entirely. Until you measure it, a qubit holds a blend of 0 and 1 at the same time. That blended state has a name, superposition. And it's the first of two ideas that give quantum computers their power. Let's break superposition down with something everyone already understands. Let's make superposition click with something you already know, a spinning coin. A coin lying flat on the table is clearly heads or clearly tails. That's like a classical bit. But a coin spinning in the air? In a sense, it's kind of both at once, until it lands and picks one. That's exactly what a qubit does. It exists in a blend of 0 and 1 simultaneously, a state called superposition, right up until the instant you measure it, at which point it lands on one definite value. Quick tangent, because you've probably heard this one. Isn't this the cat thing? In 1935, physicist Erwin Schrödinger imagined sealing a cat in a box with a 50-50 chance of a random event ending its life. According to the quantum rules, until someone opens the box and checks, the cat is technically in a blend of alive and dead. But here's the twist. Schrödinger meant this as a joke, to show just how absurd superposition sounds when you scale it up from tiny particles to something as big as a cat. Qubits really do this. Cats, thankfully, do not. Now here's where it gets genuinely spooky. Two qubits can become entangled, linked so tightly that measuring one instantly tells you something about the other, no matter how far apart they are. Einstein hated this idea so much, he called it spooky action at a distance, and spent years trying to prove quantum mechanics was incomplete because of it. A simple way to picture it: imagine two magic dice that always land on matching numbers, no matter how far apart you roll them. That's the flavor of what entanglement does. So why do superposition and entanglement matter together? Because when you link qubits, their blended states combine, and every single qubit you add doubles the number of combinations being explored simultaneously. 1 qubit gives you 2 states. 2 qubits, 4. 3 qubits, 8. Look at how fast this climbs. This is exactly what turns that try one at a time wall we hit earlier into a problem a quantum computer can attack all at once. And if you think that chart looks steep, wait until you see where this pattern leads. Let that sink in. Just 300 qubits could represent more possible states than there are atoms in the entire observable universe. Not the planet, not the galaxy, the entire observable universe. That's roughly a 1 followed by 90 zeros. This is the scale of computational space we're talking about when a quantum computer is running at full power. So if this is so powerful, why isn't there one sitting on your desk right now? Because qubits are incredibly fragile. The tiniest vibration, a bit of stray heat, even a single photon of light can knock a qubit out of superposition, a problem called decoherence. And once that happens, the calculation is ruined. That's why today's quantum computers are kept colder than outer space, near absolute zero, isolated from virtually all vibration and electromagnetic noise. And even then, errors still creep in. Managing that fragility is the single biggest engineering challenge in the field today. Let's talk payoff. What could these things actually do? Simulating molecules to design new medicines that classical computers simply can't model accurately. Discovering new materials, better batteries, better solar cells, room temperature superconductors. Untangling massive optimization problems in logistics, traffic, and finance. And on the security side, potentially breaking some of today's encryption, while also helping us build the unbreakable encryption of tomorrow. Right now, in 2026, this isn't science fiction. It's an active global race. IBM, Google, Microsoft, and others are all racing to build bigger, steadier quantum machines, each betting on a different way to physically build a qubit. One real recent breakthrough, Google's Willow chip demonstrated that adding more qubits can actually make error correction better instead of worse, which matters enormously since errors have always been quantum computing's biggest obstacle. That said, we're still early. Today's best machines run a few hundred qubits. Truly world-changing systems may need thousands to millions. There's a long runway left to run. Let's clear up a few myths before we go further. Myth: quantum computers will replace your laptop. Reality: they're specialists built for specific problems. Your laptop's job is safe. Myth: they're just really fast regular computers. Reality: they don't work faster in the same way at all. They work completely differently, exploring many paths simultaneously instead of one path quickly. Myth: we'll have one on our desk soon. Reality: this is still highly experimental technology. For years to come, you'll access one through the cloud, not buy one off a shelf. Here's why any of this should matter to you personally. Your privacy. Powerful future quantum computers could eventually crack today's encryption, which is exactly why quantum-proof security standards are already being built right now, before that day arrives. Your health. Faster molecule simulation could mean new medicines reach patients years sooner than today's slow trial-and-error drug discovery process. And your world more broadly, better batteries, cleaner energy, and smarter logistics could all get a quantum-powered boost in the years ahead. Let's pull it all together. A qubit blends 0 and 1. That's superposition. Linking qubits together, that's entanglement. Together, they let a quantum computer explore an exponential number of possibilities simultaneously, turning problems that would take classical computers longer than the age of the universe into problems that might be solved in minutes. That's the entire idea, start to finish. Let's recap the key takeaways. Classical bits are stuck at 0 or 1. Qubits can blend both at once through superposition. Entangled qubits stay linked no matter how far apart they are. Every qubit you add doubles the states explored, so the power grows exponentially. Qubits are fragile, which is why today's quantum computers need extreme cold and total isolation. And no, they won't replace your laptop, but they could genuinely transform medicine, security, and more.
All right, I promised you a mind bender, so here it is. A qubit only picks a value of 0 or 1 the moment something measures it. But what actually counts as measuring it? Does it have to be a scientist looking at a screen? Or does a single stray photon bumping into the qubit count just as much? Here's the uncomfortable truth. Nobody fully agrees. This is known as the measurement problem, and it remains one of the biggest unsolved mysteries in all of physics. So, does the universe only decide what happens when we look? Or is something even stranger going on? Nobody knows for certain. Not yet, anyway.
That's a wrap. Seriously, if you followed all of that, you now understand quantum computing better than the vast majority of people ever will. If this helped things click, drop a like, subscribe for more mind-bending science made simple, and let me know in the comments, what's your theory on that last question? Thanks so much for watching, and I'll see you in the next one.